Hello everyone, my name is Khaled Ahmed, and I'm here today to present our work, Mandoline, Dynamic Slicing of Android Applications with Trace-Based Alias Analysis. This is a joint work with my supervisors, Mieszko and Julia Rubin from the University of British Columbia, Canada. One of the challenges of developing Android apps is discovering and dealing with bugs. For example, the Memento app is an app from the Google Play Store which allows the user to set notifications for special dates. The version 11.2 of this app crashes when the user sets a reminder for the 30th of February, which is a non-existing date. A developer interested in finding the bug will most probably start debugging from the statement at which the app crashed in the code. In this case, it would be the statement that creates the date object, which is new date that we see on the slide. Then, they will attempt to find statements in the code that lead to the crash. These statements include the definition of the variables day, month, and year. But for now, let's say the developer focuses on the day variable. They will attempt to find the definition of the variable day, which is set to user input.d. User input is passed as a parameter to the method. The same parameter is called selected in the method that calls foo, where the value of the field d is actually set to the value returned by picker.getValue method. And the value is picked from an array inside the picker framework code, which is created as an array from 0 to a maximum value set by the developer. In this case, the value set by the developer is 31, which causes the crash as the user should not be allowed to enter 31 for the month of February. This activity can be automated by the process called slicing, which will find statements related to the crash site. When slicing is done for a specific execution, it is called dynamic slicing. The slice, which is in this case shown on the slide, is smaller than the entire code, making the debugging process easier as the developer can direct the focus on the lines that lead to the crash. The main challenge for dynamic slicing is to automatically track data flows between statements. As for any slicing technique, tracking data flows between fields is challenging. That is because the field can have two different names, like in this example. The simple solution to this problem, which is applied by most, if not all existing dynamic slicing approaches, is to instrument and record memory addresses of all fields accessed by the app. This solution does not work in Android, as such instrumentation will slow an app down, and Android will simply kill slow apps due to unresponsiveness, which makes debugging impossible. Another Android-specific problem is that applications are not self-contained and they rely on Android framework methods. So we need to track data flows through framework methods. And this would require instrumenting the entire Android framework, which is not really practical. So, to solve this problem of data flows in fields and in the framework for Android, we propose to use lightweight instrumentation on device, then do a sophisticated analysis directly on the produced trace to extract field data flows. Also, we propose to use statically constructed framework models for framework data flows. For trace-based field analysis, our goal is to find field data flows without relying on object addresses. The main challenge in doing that is how to produce a trace with lightweight instrumentation. Also, what kind of information can we use from the trace to find field data flows to replace the need for object addresses? First, let's look at this piece of code. In line 1, we assign the value 15 to the age field of Jane. Then in line 2, we assign Jane to John. In line 3, we set the age field of John to 25. Then we assign Jane's age to the result of this block of code. Now, let's try to find the last modification to the field Jane.age that is used at line 4. I'll pause a bit to let you look for this modification. Okay, let's now look for how to automate finding this modification. A naive approach would be to look for the name Jane.age on the left-hand side of an assignment. So, since the modification is always before the use, let's go back in the trace and look for Jane.age. We find the modification at line 1, but that's not actually the correct modification of the field, and that is because at line 2, the variable John alias is Jane, which means that John.age at line 3 also aliases Jane.age, which makes line 3 the actual modification of the field, since the assignment to John.age is also an assignment to the field that it aliases, which is Jane.age. Our solution to this problem is to first do lightweight instrumentation to get the trace, then do field alias analysis. Our instrumentation records an identifier for each statement to a log, and then we recover the actual code from the statement identifiers. We also do an optimization where we only do this instrumentation once per basic block. Our insight is to use field alias analysis as performed by static analysis techniques, but on the execution trace instead of the source code of the app. This analysis starts from the use of the field, then goes backward on the trace to look for either the modification of the field or assignments that cause the field to alias other fields. At every line, the analysis decides if it should look for other variables too. For example, here the analysis decides that it should search for the modification of the field John.age. The analysis also decides in which direction it should look for the field. For example, the analysis should not search for the field John.age in the backward direction, because the aliasing of John to Jane only occurs at statement 2 and may not be true before that statement. Instead, the analysis should look for the variable in the forward direction, which leads to the correct modification of the field. So, this algorithm goes in both backward and forward directions on the execution trace to look for the field modifications. The full field alias analysis algorithm is explained in the paper. And in summary, the algorithm has three main components. The first component is the backward analysis that traverses the trace backward. The second component is the forward analysis that looks for modifications of fields in the forward direction. The last component is to check every statement and decide on the variable to search for and which direction to search for them. Next, I'm going to explain how we detect framework data flows. The main challenge is to detect these data flows without instrumenting the framework. To address this challenge, instead of using dynamically extracted data flows through instrumentation, we use the statically constructed data flows of StopDroid and FlowDroid models that capture the propagation of taints within Android and Java framework methods. Both approaches capture the propagation of taint through the framework methods by mapping tainted inputs to tainted outputs. More specifically, they track the propagation of taints from method parameters, receiver object, and their fields to the parameters, receiver object, the return variable, and their fields. For example, here's the method set01 of the pair class. It sets the first member of the pair to the value variable that is passed as a parameter. In this method, if the value parameter is tainted, the taint propagates from the value parameter to the field that's called first of the receiver object. If the value parameter is not tainted, the field first of the receiver is not tainted either. This is captured by the taint propagation rule from value to this dot first. But no taint propagates from the receiver or any of its fields to any other variable or the return of the method. So there are no taint rules for these variables. Another example is the method getO1 of the pair class. This method returns the field first of the pair. So the taint propagates from the field first of the receiver to the return of the method. And the rules of these two methods are completely different. What FlowDroid and StubDroid framework modeling do is that they complement each other and provide accurate taint propagation rules for most Java and Android framework methods. However, a slicing algorithm works on assignments, not taint propagation. And since the taint propagation implies a flow of data between two variables, we represent this taint propagation as an implicit assignment, which captures a flow of data between the two variables. The assignment does not necessarily capture the actual modification to the variable, but this assignment exposes modified and used variables by the method, which is all what the data flow analysis of the slicing algorithm needs. Now, let's look at this example for how to use this modeling for data flows. Here, we set x equal 5, then set the first element of the pair as the variable x, then assign y to the first element of the pair. Now let's say we want to establish if there is a data flow between x and y in this code. The model of setO1 method is the assignment from the parameter x to the field first as we saw before. And similarly, the getO1 method is modeled as the implicit assignment y equal pair.first, which we create from the StubDroid and FlowDroid taint propagation rule. So the data flow that reaches y comes from the field first in the getO1 method, which has a data flow from the parameter x of the setO1 method, which in turn has a data flow from the definition x equal 5. And that's basically how we track data flows through framework methods. More details are in the paper. Putting it all together, here's the high-level overview of our entire solution, which we call Mandoline. Mandoline has the basic pipeline of dynamic slicing tools. It starts with a static analysis component that instruments the Android app. The instrumented app is run on device, and the execution is either derived manually or by a test script. Then the execution trace is extracted from the app. The trace is then parsed to create a statement graph, and finally, we slice the statement graph using the classic slicing algorithm. We extend this algorithm with field alias analysis and framework modeling. The algorithm creates a slice from a user-selected statement and variables used in the statement, which is called a slicing criteria. We evaluated Mandoline in terms of accuracy and performance. We asked two research questions. How does the accuracy of Mandoline compares to the state-of-the-art in dynamic slicing for Android? And we asked the same question for performance. The subject apps are 12 applications from the app benchmarks DroixBench and DragDroid, which are the most recent datasets of faulty apps that crash. We selected the apps where the crashes are reproducible, and we selected these benchmarks since the slicing criteria is easily identifiable as the statement that crashes the app. Our baseline is ANDROIDSLICER, which is the state-of-the-art in slicing Android apps. It is in fact the first dynamic slicer for Android apps, which focused on solving the problem of data flows across callbacks. However, it misses data flows in fields and in the framework. We implemented ANDROIDSLICER++, which fixes implementation issues with the provided implementation of ANDROIDSLICER. We also made the instrumentation on par with Mandolin, and that's to allow fair comparison to Mandolin and to highlight the benefits of field data flows and framework modeling. We contribute AndroidSlicer++ by making it publicly available. We compare Mandolin to both AndroidSlicer and AndroidSlicer++. To create the ground truth for evaluating the tools, we manually produced slices of bugs from these 12 applications. The manual slices were cross-validated by 2 researchers in our group, so we're fairly certain it's a reliable benchmark. This benchmark is the first of its kind because it's the first set of slices for bugs in Android apps. And it's useful since the state-of-the-art only compared slice sizes to trace sizes, which does not show the accuracy of the slice due to the absence of such benchmark. We hope that future slicing techniques for Android apps can use this benchmark to evaluate their approaches. We compared the accuracy of Mandolin to both the provided version of Android Slicer and its enhanced version Android Slicer++. We compared the accuracy using the F-measure metric, which measures how many statements from the manual slice are in the tool-produced slices and how many statements that are not in the manual slice are not in the slice produced by the tool. In this shown graph, the black dots show the F-measure of each app. The boxes shows the quartiles of the F-measure of the tools. The figure shows that the average accuracy of Mandolin is above 80%, which is almost twice that of the improved Android Slicer and 4 times that of Android Slicer. We also compared the on-device instrumentation overhead of the tools. The figure shows the overhead of Mandolin versus Android Slicer. We omit Android Slicer++ since it has the exact same instrumentation as Mandolin. Mandolin and the enhanced Android Slicer++ have 10 times less overhead than Android Slicer. We also compared the slicing time of the 3 tools on the host PC. Mandolin has a higher off-device slicing time, which is due to the added field alias analysis and the framework modeling. Also, Mandolin produces bigger slices, which means it processes more statements than Android Slicer. This added off-device slicing cost is a maximum of 16 minutes. But we believe this slicing time is acceptable given the huge improvement in accuracy over prior work. To summarize, the first contribution of this paper is Mandolin, an accurate dynamic slicer with field alias analysis and modeling of framework methods. We also contribute the first benchmark suite of manually produced slices of Android apps. We make the implementation and benchmark suite publicly available. Please feel free to contact me if you have any questions about our tool. Thank you for listening and have a nice day.